Here I'm going to model how to do a confidence interval for a proportion, or sometimes we call it a z-interval. So what we have is we have a local newspaper has polled some of the voters, 330 voters, and look, it's a random sample. Okay, so that's great. They found that 144 of these people say they're going to vote yes. Okay, so that's our success. We're going to define yes as being success in this case. So this is for an upcoming school budget. So they want us to create a 95% confidence interval for the actual sentiment of voters. Okay, or it's, in my words, we want to estimate the true population of all the voters. Okay, so let's record a couple things. The sample size, which I always use n, so the sample size is 330, so we're going to use that. And p hat is our sample proportion. So that's going to be the number of successes. Oftentimes we use x. The calculator uses x. So it's the number of successes divided by the sample size. So that's 300, no, sorry about that. It's not 300, it's 144 divided by 300. And I believe that's 0.436. Okay, so almost 50%. Okay, so before we calculate a confidence interval, remember that a confidence interval is an estimate plus or minus a margin of error. Okay, so before we calculate this, though, we have to make sure that the normal model applies. All right, so to do that, we have the independence assumption that we have to validate, and we have what I call the sample size assumption that we have to validate. To do that, we look at certain conditions. So there's sometimes 3 that we have to check for the independence assumption. So here, what we do with this plausible independence condition is basically we justify that we think, in our opinion, why these voters are independent in this case. So we're going to say that something like it is reasonable to believe those selected for the survey were independent or their opinions were independent. Let's say providing proper survey procedures were deployed, something like that. Okay, so it's reasonable in this case to believe that each person sampled they're not going to affect the opinions of other people, providing that they do the things that we learned in first semester. Okay, so now how about the random sample condition? Well, don't just say yes. At least say something. So yes, they were randomly sampled. I know throughout this course it seems like I've been very picky, but that's how they are in the AP test, so that's how I have to teach the course. So you could say yes as stated in the problem, but sometimes it's not stated, so you have to assume. And by the way, if it's not a random sample, then check to see if it's reasonable to think that the sample is representative. If so, maybe you can proceed that way. Okay, 10% condition. So here, they didn't tell us the size of this voting population. They just said it's a local newspaper and local ballot for a school budget. So we really don't know if it's a if it's a small town or if it's a big city or something in between. So let's just recall that the sample size needs to be less than 10% of the population size. Well, let's just call that S. So what we could do is we have N, which was 330, has to be less than 10% of, in math is multiply. Okay, so let's just say S. So you divide by 0.10, and we get the population has to be greater than 3,300. So let's just say yes, providing the voting population is greater than 3,300. Okay? Does that make sense? Hopefully it does. Let's see. Now, the sample size condition. Don't get that confused with the 10% condition. Here, the 10% condition, we want it to be less than some amount. But here, we need to make sure that the sample size times p hat is greater than 10. Okay, and we need to make sure, so that's the number of successes is greater than 10, and we need to make sure there's no such thing as n hat, n times q, so the number of failures is greater than 10. Okay, so here we have 330 times 0.436. We want to check to see if that's greater than 10, and it is. That's going to be 144. It's greater than 10. So that's true. All right, and then 330 times 1 minus 0.436. Okay, so that's 330 times 0.564. Greater than 10, greater than 10, and I believe it is. Yes, 186 is greater than 10. Okay, so it's a lot of work, but you have to do this. It's part of AP Stats. So before we proceed, we make what I call a transition statement. We're going to transition from checking the assumptions to doing the calculations. So we would say something like the conditions are met. Are satisfied. So we will proceed using a normal model to create or compute a 1 proportion z interval. Okay? So now we can do the computations. So let's just recall that we have a confidence interval is an estimate plus or minus a margin of error. So the estimate is p hat, We took a sample, we measured the proportion, that's our estimate. The margin of error is this thing we call the critical value, okay, and times what we refer to as the standard error of p hat. It's like the standard deviation, but it's an estimate of the standard deviation. It's the best we can do. Okay, so p hat, let's see, hold on, I'll plug this in a minute. So you don't have to do all these steps, but I'm in teacher mode, so let's just leave it right here for now. This is going to be the square root of p hat times q hat all divided by n. Okay, so this is probably where you need to start, but I'm, again, in teacher mode. So we get 0.436 plus or minus, I'll come back to this in a minute, times the square root of 0.436 times, what was it, 0.564. It's just 1 minus p hat, divided by 330. Let's make sure that's all underneath. Okay, so to get z star, if you don't remember, it's not that hard to figure it out. What you do is just draw a normal model and perfectly symmetric, just like mine. That's a piece of humor, by the way. Okay, so we know that they want us to calculate a 95% confidence interval. So there's 95%, right? We're estimating that this is the center. So if that's 95%, then the stuff left over is 0.05, right? 0.05. So if we divide that by 2, we get 0.025 and 0.025. Okay, so z star is simply equal to inverse norm, and put in 0.025, and what you'll get out is a negative 1. Let's see, what do you get? 1. I just had it. I'll have to do it. Second, so you do second distribute and inverse norm 0.25. Hold on, my calculator is messing up, right, in my video. Okay, inverse norm 0.025. I know, I should have known this. So it's 1.95996, so negative 1.960. All right, and we don't need the negative. I mean, this would be positive 1.960, and this is negative 1.960. So it doesn't matter because we're going to do plus or minus, so it's 1.960. All right, so now we can do the computations. I'm going to get, if you're checking your work, I get 436 plus or minus 0.054. Okay, and sometimes we write the confidence interval is 0.383, and put a comma in there, 0.49. All right, so we're almost done, but we have to interpret the confidence interval. So what we say is it's kind of a standard thing, just like when we do simulations, we say according to the simulation. So here we're going to say we are 95% confident that between 38.3% and 49.0% of the voters will vote yes on the upcoming budget. Something like that. Okay, so the key is to say we're 95% confident. Okay, this is to interpret the confidence interval. All right, so that's basically the first example. So give that a try.